You know, for decades, tech progress meant faster chips, bigger hard drives. But what we're talking about today, it's a whole different ballgame. We're talking about a technology that literally speaks the language of atoms. One that could solve problems we used to think were, well, impossible. Today, we're decoding the quantum leap.
So how are we going to break this all down? First, we'll get a handle on what this new quantum revolution actually is. Then, we're going to meet the main villain of our story, a little problem called noise. After that, we'll look at the global race to build new hardware and smarter software to fight back. And finally, we'll get to dream a little and explore the incredible world that's waiting for us if we win.
All right, part 1, the second quantum revolution. For about 100 years, quantum physics was something we just studied. Now, it's something we're starting to build with. We're actually learning to speak the universe's most fundamental language. And believe me, that opens up a whole new world.
I know, this looks like something straight out of a sci-fi movie, right? But it's real. This incredibly complex tangle of wires and tubes, that's the heart of a quantum computer. We have officially entered an era where we're not just looking at the quantum world, we're reaching in and actually controlling it. So what does that actually mean, quantum technology? Well, put simply, it's about using the weird and wonderful rules of quantum mechanics to build stuff. Stuff that can compute, communicate, and sense the world in ways that are just fundamentally impossible for the classical computers in our phones and laptops. And this slide really nails the key difference here. The first quantum revolution was all about understanding the rules. That's what gave us things like lasers, for example. But this second revolution, this is about actively manipulating those rules. It's like the difference between just admiring the power of the ocean and actually building a surfboard to get out there and ride the waves. Which brings us to part 2, the noise problem. Because for all this incredible promise, there is one giant obstacle standing in our way. It's a fundamental challenge that scientists all over the world are just racing to solve. They call it the noise problem. And that leads to the really obvious question, doesn't it? If this tech is so powerful, what's the catch? Why isn't it everywhere already? Why don't you and I have one sitting on our desks? Well, the answer, the main villain of this whole story, is noise. A quantum state is an unbelievably delicate thing. I mean, the tiniest vibration, the slightest change in temperature, literally anything can disrupt it, create errors, and just ruin the entire calculation. It's like trying to build a really beautiful, intricate sandcastle right as the tide is rolling in. This is what leads to the two big categories you're seeing here. Right now, today, we are in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. Think of these as brilliant, but really, really fragile prototypes. The Holy Grail, the place we're all trying to get to, is FTQC, fault-tolerant quantum computing. Those are the machines, the reliable, powerful ones that will finally be able to solve those world-changing problems. And you better believe the race to solve this is heating up. Just look at these charts. They show the number of research papers published on fault tolerance and error correction. See that huge spike right around 2019? Yeah, the entire global scientific community has gone all in on cracking this noise problem. And all this intense focus, it's starting to pay off. As Cecile Perrault from the quantum company Alice and Bob puts it, FTQC is no longer a distant goal, it's on a defined trajectory. This isn't just wishful thinking anymore. People are creating actual concrete roadmaps to get there.
And that brings us to part 3, the race for hardware. Because if you want to beat noise, you need a much better foundation. And that means building better, more stable quantum machines from the ground up.
So how do you even build one of these machines? Well, it turns out there's no single recipe. It's a wide open race with a bunch of totally different approaches. You've got some, like superconducting qubits, that are incredibly fast but have to be kept colder than deep space. Others, like trapped ions, are super stable but also kind of slow. Every single one of these technologies has its own challenges and its own champions. And right now, honestly, nobody knows which horse is going to win this race. It all really boils down to what Dr. Kees Eichel of Quotech points out here. It's not just about getting more qubits, you also have to have better qubits. He says the quality of qubits and better integration are two sides of the same challenge, scaling up. You see? It's a battle on two fronts at the same time, quantity and quality. But look, building better hardware is only half the battle. Which brings us to part 4, making these systems smarter, stronger, and connected. Because if the hardware is the engine, you still need a clever driver and a great GPS to get you where you need to go. So to get the most out of today's noisy machines, scientists are getting really creative with 3 main strategies. First, they're creating these hybrid teams, pairing a quantum computer with a regular supercomputer and letting each one do what it does best. Second, they're basically using AI as a quantum coach to help optimize how the whole thing runs. And third, instead of trying to build one giant perfect machine, they're connecting a bunch of smaller ones together into a really powerful network.
So maybe think of it this way. If the quantum hardware is our hero, then all this clever software and all these new connections, those are the power-ups. They're what take today's noisy machines and turn them into something that can actually start solving some incredible problems.
And that third point, the one about connectivity, well, it's turning out to be way more important than anyone first realized. As Jesse Roberts puts it, the quantum computing ecosystem underestimated the value of connectivity for scalability. It turns out, trying to build one single, perfect, massive system is just incredibly hard. The future probably isn't one giant brain, it's a network of connected ones.
And that brings us to our final section, the world of tomorrow. Okay, let's say we do it. We solve the noise problem, we build the hardware, we connect it all together. What's the big payoff? What does this all actually unlock for us?
Well, the payoff could be immense. We're talking about designing life-saving drugs by perfectly simulating molecules, a process that takes years today. We could create brand new materials that might revolutionize batteries or help capture carbon right out of the atmosphere. We could solve mind-bendingly complex logistics problems for shipping companies or financial markets. And maybe, just maybe, we could build a truly unhackable quantum internet.
And this isn't just about cool science, it's about economics. To give you some perspective, just one small slice of this new world, quantum sensors, is projected to be a €6 billion market within about a decade. This is not some niche academic field anymore. This is the foundation of a brand new global industry.
So when you put all of this together, the progress, the investment, the sheer brain power being focused on this one problem, it becomes pretty clear. The quantum age is no longer a question of if. It's really just a question of when. And that, of course, leaves us with the biggest question of all. Are we ready?